This video is about reaction mechanisms or how the reaction proceeds. You should already be able to identify reactants and products, combine reactions to make an overall reaction, and explain what a catalyst does to a reaction. But by the end of the video, you should also be able to identify catalysts and intermediates in a reaction mechanism, find the overall reaction and define its molecularity, and last, write rate laws based on the rate determining step. So the question in the video is, catalytic converters we saw before in cars decrease the air pollution by converting NO and CO to N2 and CO2. But do all the species actually collide at the same time to create this reaction? Do we have two COs and two NOs colliding at the appropriate energy and orientation in order to magically make N2 and CO2? Or is it the process of reactions that have to occur in order for this whole reaction to take place? So let's talk about reaction mechanisms. The overall progress of a chemical reaction can be represented at a molecular level by a series of elementary steps, or smaller steps that need to take place. The sequence of the elementary steps lead to a product formation called a reaction mechanism. So if the overall reaction is that two NOs react with an O2 to make two NO2s, that does not mean that is the only thing that happens, that two NOs magically hit oxygen all at the same time, all at the right speed and orientation. What really happens is that this can happen in multiple steps, right? N2O2 is actually detected during this reaction, even though it's not in the overall reaction. So there has to be an N2O2 being formed at some process. If you look into more detail, you'll find that NO and NO first react to form N2O2, the thing that we can detect without actually seeing an overreaction. The N2O2 then reacts with the oxygen that we set as a reactant, and that forms the NO2. The N2O2 is what's called an intermediate because it cancels. It was formed and then immediately used later in the reaction. An intermediate can cancel out so that you can form the reaction that we had overall. NO can be reduced to N2NO. The O2 is still before the arrow. These are all still reactants, and that's still a product. So the elementary steps sum up to the overall reaction. So intermediates that we just canceled out are species that appear in a reaction mechanism, but not in the overall balanced equation. An intermediate is always formed in an earlier elementary step and consumes in a later elementary step, as we saw before. So the N2O2 was the intermediate. In a reaction mechanism that we saw before, the reactants may be higher or lower than products. This is showing an exothermic reaction. The EA, or activation energy, is how much energy it needs to take in order to get over the hurdle and start the reaction. In this reaction, there's actually two reactions going on. So in that case, the first elementary step might have been higher or took longer than the second elementary step. This part, it represents the intermediate, or the N2O2 that formed. So it had one reaction and then another reaction. It's almost like a roller coaster, right? A second word that we need to know about is catalysts. We talked about them briefly before, but now we have to see them in reaction mechanisms. So catalysts speed up the reaction and refine the reactants for first elementary step, and then a products later in the last step. So if you look at this reaction mechanism, A and C react to make AC. Then AC immediately was used, that means it's an intermediate, to react with B. It made ABC, and that ABC immediately decomposed, so ABC is another intermediate, that formed A, B, and C. So the C that we put in at the beginning, the first elementary step, came out unharmed at the end of the process, which means I can reuse it, and therefore it is a catalyst that sped A and B reacting up. I know it looks like it took a lot longer, but it actually means that it went faster. Maybe A and B didn't collide the right way this whole time, and the catalyst made it so that A and catalyst reacted, and then that reacted to form B. A catalyst is homogeneous if it's in the same phase as other reactants. If not, we'll call it heterogeneous. So with a catalyst, originally A and B might have reacted to form the progress, and it took a lot of activation energy to do that. The catalyst will decrease the activation energy in order to make it faster, a reaction, even though the reaction itself stays the same. A and B and C and D are still there. The types of steps that we're looking at, these elementary steps, are called uni, bi, or termolecular. It just means how many particles are colliding at any moment. If there's only one particle before the arrow, literally the coefficients of 1, then it's called unimolecular, and the rate law for that is K times that A. If it's an elementary step in which two particles are colliding, or 2A, or two different particles colliding, A and B, those are called bimolecular. Notice that their rate laws for elementary steps are determined by how many particles are colliding. So this time we do care that the coefficient is 2 because it is going to be an elementary steps rate law. We used to write rate laws dependent for the whole reaction. We're dependent on data, right? But for rate elementary steps, it's dependent on how many are reacting, so the molecularity. Let's do it for term molecular. Term molecular can mean A and B are reacting, or 2A and B, and therefore you look 2 A's and a B. Or it could mean that there's 3 different things, A, B, and C, so A, B, and C. So term molecular is probably a little less convenient because they would have to react at the same time with the right orientation and energy, but if it did react, this is what it would look like. So again, the powers are determined by how many there are only in elementary steps. That's really important. And the rate determining step is the slowest of those elementary steps. It will have a similar rate law as the overall reaction rate law. So if we looked at an example of NO2 and CO making NO and CO2, the rate law was found experimentally by, going through this one doubled first order, this one tripled first order, that kind of thing. And they got rate equals K NO2 squared. So what they're telling us is that NO2 affected the rate twice as much, and CO didn't affect the rate at all. And in that case, that means that this is not the way the reaction proceeds. It must be proceeding in maybe a series of elementary steps. CO is necessary for the reaction to occur, but the rate did not determine on it. So maybe the steps might have been something like this. Maybe where there's one NO2, there's multiple NO2s, right? Because we probably have a mole of it. So maybe those NO2s collided first. They made NO3 and NO, which was a slow step. This is why it affected the rate. It's the rate determining step. And then the NO3, that intermediate is what reacted with CO. And that was fast. And that's why CO did not affect the rate, because it was really quick, like within seconds, milliseconds. And that formed the products we saw here in CO2. Because if you combine these two, the NO3 will cancel out, and you'll get the reaction we had before. So NO3 is an intermediate consumed. As CO is not involved in the slow rate determining step, it did not appear in the rate law. You should also be able to create rate laws for each step in a mechanism. So if they say this is the mechanism, we would write a rate law for each one. So for the first one, a rate equals K, HBr because there's one of those, O2 because there's one of those. For the next step, it would just be rate equals K, HOOBr because there's one of those, and HBr because there's one of those. For the next step, it would be rate equals K, HOBr times HBr, and the last step, rate equals K, HOBr times HBr. Notice that the overall reaction was a sum of all these 4 little reactions, and experimentally they found that the rate was equal to K HBr times O2. That means that remember, the elementary steps, their orders are determined by how many are there, and there was one of each, so there's all first orders. But the rate law for the overall was found by doing that same process of this doubled, this is first order, this tripled, this is first order, right? So this was found experimentally. It does not have to do with the coefficients. What we're going to be seeing is that the rate laws are, for the overall, match the slowest step. See how the slow step has HBr as well as O2 with the same order? And that's why it was labeled the slow step. So slow steps determine the rate law. Their rate laws should be identical. So if we wrote the rate law for this reaction, we know it's HBr times O2. And the intermediates in the reaction were things that canceled out, like HOOBr and HOBr. They canceled out, and that's why they're not in their overall reaction. There were no catalysts in this reaction because nothing went in and then came out undisturbed and was reusable. So there's a little bit more of a nuance with reaction mechanisms. So we're going to get into a little more detail. Given this overall reaction of H2 and I2 makes 2HI, the first step is that iodine actually breaks its bonds to form 2I. It happens pretty quick as long as it's warm enough. Then the H2 that we had in the reaction reacted with those 2 I's, and that's what formed 2HI. So H2 does not collide with I2, right? And we found experimentally that the rate was equal to K times H2 times I squared. So what we're wondering is, that rate expression is not acceptable because it's an intermediate is listed in the rate law. So like if you had written the slow step as, from here, right? The slow step would have given you this rate law, right? To the K of step 2, H2 times I squared. So what we're saying is, right now it doesn't look like the slow steps rate law equals the first steps rate, the overall rate law, right? Because the overall rate law might be H2 times I2. They don't have the same species. So that means that we have to do a little bit of moving around. Consider that the first step was a reversible reaction. When it's reversible, you can read it forward and reverse. And it was fast step. because of that. So that means we can write two rate laws for that. The forward rate law, which would be Kf, forward, of I2, and then we can also write the reverse rate law, which would be Kr, reverse, of I squared. Why? Because I is in the, if you read it backwards, would be the initial or reactant, and there's two of them. So remember, for elementary steps, you just put that as its order. If I rearrange this equation, I would get Kf over Kr is times I2 equals I squared. And if we substitute this in the previous rate law we had before, which was rate equals the slow step times H2 times I2, we can, instead of using I2, we can put in Kf over Kr I2, and it becomes this. Hey, don't those have the same species as the reactant, the overall reaction? It does, which means it is consistent. I just had to modify some stuff. But what I'm saying is, going back to the previous slide, since this fast step is reversible, I can read it forward or reverse, and I can substitute species in to make sure that the slow step is in fact a slow. Let's do this again. It's usually easier if you see this in more detail with more examples. Ooh, things are just popping up all over. So the overall reaction for a reaction of 2NO and F2 makes 2NOF2 and has an experimental rate law of K equals NO2 times F2. The accepted mechanism is that the NO2 reacts with fluorine to form these intermediate species in a slow step, and the NO2 again reacts with the fluorine, and that's what makes NO2F2, F, in a fast step. Notice that the overall reaction is still what I wrote up here, and the species that are in the slow step match the species that are in the overall. So we have a series of checklists we should make sure where it's happening. The elementary steps sum to the overall, yep. Both steps in the bimolecular are therefore reasonable, right? So there's two things here, and there's two things in the overall, yep. And the elementary rate law would be the same species as the overall. So if I wrote it for the slow step, it'd be NO2 times F2, which was consistent with NO2 times F2 in the rate law. So this mechanism is reasonable. If we look at a second example, the overall rate law of N2NO plus O2 makes 2NO2 has an experimental rate law of NO2 squared O2, and they gave this experimental mechanism. They're saying NO reacted with O2 made NO3, and then that immediately reacted as an intermediate with another NO, and that's what made NO2 in a slow step. Then what we have to worry about is the fact that the slow step does not have the same species. The NO3 does not match the NO here. The NO does, but we don't have oxygen here. So we don't have the same species in the slow step and the overall step. So we do have a sum working out. We do have that they're both bimolecular, but they're not the right substances. So we have to do a little finessing, right? So again, these were the reactions that were given, the elementary step 1, the elementary step 2, and the overall. I just rewrote them for you. And if we wrote the rate laws for these, rate laws would be determined by the reactants, NO and O2, and here NO3 and NO. And I just wrote K1 for step 1 and K2 for step 2. Remember that the first step is reversible, so that means I can also write it reversed. So the K1 going backwards would just be dependent on NO3. And that means these two rates are equal because forward equals reverse because it's at equilibrium. So I can rewrite it as K forward NO times O2 is equal to K reverse NO3. They're equal to each other. And I can rearrange that and I can solve for NO3. So I just divided by KR. NO3 is now alone. What that means is now I can substitute NO3 in for this rate 2. So if I take rate 2, which used to be NO3 times NO, and I substitute all this in for NO3, I get K2, KF, KR, which is a whole new K, NO times O2, which was substituted in, times NO that was originally there, right? Originally was already there. I can rewrite that as NO times NO, or NO squared. Hey, that is the rate law, right? So I'm modifying the equation. This might seem really confusing to you, so I'm going to go through a summary and we'll try a lot in class. The elementary steps must add it to the overall. The rate determining step, or the slow step, must determine the rate law. Overall rate law orders are found through experimental, not by coefficients. But the elementary steps in the rate determining step have rate laws that are determined by their molecularity or coefficients. Any reversible reactions will have a forward reverse rate equal to the reverse rate, and therefore a forward rate law equal to its reverse rate law. And this can be used to substitute intermediates. And a mechanism is a hypothesis. We cannot prove it is correct, but we can use consistent data and show that the predicted results accurately follow this model for this reaction. So back to the question in the video, do two NOs react with two COs all at the same time? Definitely not, because that would be tetramolecular. So what they do is they use PD, PT, and RH as catalysts to make this reaction go faster. First, the NO breaks down into N2 and O2. The CO reacts with those O2s as an intermediate and forms CO2. I'm going to rewrite this so it's balanced. So right now it wasn't balanced, so I just have the N2 and the O2. Same thing here, I need to balance this, so use half of that amount. And therefore you can see that these are intermediates, and if I sum it, I get the overall reaction. So that is just happening twice as much. If I don't want the halves, I can just see it happening twice as much. What I'm saying is this is not what happens. What happens is the NO decomposes, the CO reacts with some of that decomposition, and it actually happens maybe half as much with an intermediate and a catalyst involved. At this point, you should be able to identify catalysts and intermediates, find an overall reaction by summing their intermediate steps, determine molecularity, and write overall rate law based on a rate determining step.